So before we start the kinematics, I would like to just give you a preview of or the motivation why we need to learn this particular chapter. So anyone of you who knows what is kinematics?
Physics related to motion.
Pardon?
Physics related to motion.
Yeah. Okay, of course. So what is the essence of kinematics? So of course it's a branch of physics, okay, which deals with motion. But there is one subtle difference because we have also a chapter called Newton's laws of motion, which is entirely different from this particular chapter. So kinematics is all about understanding the future of motion, knowing the present parameters or present condition. What does it mean is kinematics give you a predictive model that will happen if these conditions are met. For example, if you know that if a car is accelerating with this acceleration, assuming this is there's a constant, and if it starts from rest, that is initial velocity is zero, then what will be its velocity after 5 seconds? Now the after 5 seconds has not happened. The event will still happen, but although the event has not happened, we are able to predict the behavior without actually letting the event to happen. So kinematics is like it gives you a predictive model about motion. Now, why it is necessary? Now, there are very instances when we can think of it. So, imagine you design a runway for the flight to either land or take off. So now, every runway, when you're trying to design on a remote location, so you cannot bring the plane and see it how fast it goes, and then decide what should be the length of the runway, which is sufficient for flight to take off. So now this designing of the runways depends on the predictive model of a airplane. So we must be knowing that what length is sufficient for the flight to take off, and for that we must be knowing at what speed the takeoff happens. We must be knowing what is the maximum acceleration that we can generate in the machine. Okay, so everything is predicted because of the certainty in the mathematical relationship, and this will allow us to actually calculate the length of the runway which is needed for takeoff, and then we design the runway afterwards. The idea is simple. We need some predictive model to think about the future. So let's say if you have a car and you want to go somewhere, so you start from rest at home, and then you want to know that after what time you will reach at your destination. Again, destination is far away. You have a car, so let's you assume something like you say that okay, if my car will keep on moving at a speed of 60 kilometer per hour, then my car will take this much time to arrive at the destination. Now this is again you're predicting. So because the distance is known, maybe you know the GPS, the distance is known to you how far it is, and if you have the predictive model that you can drive your car at one particular speed, again you know then when you're going to reach your destination. So now all these predictive models are necessary for even Google to understand how the time estimation will take place. So now Google is able to say you the approximate time that it will take, and these all are because of the predictive models. Okay, so kinematics is of course a branch of physics, but the essence of kinematics is to create the predictive model in which if I give you certain inputs called the initial condition, okay, and if those conditions are going to be mathematically valid, if that validity is present, then certainly after some time you will achieve what you expect. So that is the essence of kinematics. So you all have studied in kinematics like V equals to U plus AT, or S equals to UT plus half AT square, or V square equals to U square plus 2AS. All these things you studied, and without any realization, what you wrote those equations, those were the, yes,
अरे
what happened?
फिर बस
So
आज आज करते रहो तुम लोग, नहीं ठीक ही नहीं होएगा.
mute yourself, mute yourself. Who is there? Mute yourself. Mute yourself, guys.
So, hello, sir.
Yeah, tell me.
Sir, the kinematics revolves around the three formulas which you just V is equal to U
No,
plus
no,
CT.
no, 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 no. It's not like that. Those are the formulas which you derive upon the assumption that what if the acceleration is not going to change for the duration of observation. So if I am going to observe certain phenomena, believing that acceleration in that duration remains unchanged, then what will be the predictive model for the velocity, for the distance or displacement, not displacement, distance, displacement, and the relationship between the speed and the displacement. Now, all these three formula revolve around the very basic assumption: what if acceleration is constant? So now, what if is already there in the this predictive model? If the acceleration starts changing, then these formulas will not work. So you need to rederive a new model to predict the behavior of motion. So in our syllabus, we will learn about something called variable acceleration. So an acceleration which is changing, is not constant, and in such scenario, you won't be able to apply the three basic formulas of kinematical equation which you have already studied. In such scenario, you need to rederive mathematically using the concept of calculus. So I hope calculus is taught to you. Like, did I teach calculus? Yeah, I have taught. All right. So the calculus is the sense of all derivation. All right. Hmm. So are you guys still facing the network issues?
Yes, sir.
Okay, no problem. So let me give you the formal definition of kinematics. Now, kinematics is really powerful, and like you need to understand why it is so necessary. I gave you some practical examination where things were okay. If it is if there is no predictive model, then you will never get the idea that how long the runway must be for the secure landing and takeoff of a flight. And of course, these ideas are necessary. Let's say if you jump from the sky, so there are many adventurers called the skydivers, and they jump and they know the predictive behavior of air resistance. So when some fighter plane they are free falling, they just shut down their engine and they free fall. They know exactly at what level they must begin their engine so as to avoid the collision. So what they do is they work on the predictive nature of acceleration due to gravity, air resistance, and various other factors. So knowing these disturbance and their behavior, creating a suitable model or called you can simply say a mathematical equation. See what you're writing the equation is basically called models. Okay, so when you write V equals to E plus AD, this is called a model actually. So of course we call this model as kinematical equation, but the more suitable term would be for these equation is mathematical models which predict the behavior of motion based on the input and assumption that the acceleration is constant. But in real life, when we create the predictive model, it comes with numerous variables like air resistance, air turbulence, and various other aspects. And if we take care of all these various aspects, the motion becomes little bit tricky and difficult. So that is why when the Elon Musk is trying to land the launcher of satellite back to Earth, he is facing tremendous difficulty in stabilizing the landing actually. And the problem of this stability is because of the non-predictive behavior of air resistance and air turbulence. So in general, you may think of gravity as a constant parameter that how gravity works is known to us in advance. But air resistance and air turbulence is a big issue, even for him to balance. So he has created various algorithms which can take care of all these variability to make a predictive model so as to land the launcher back to the Earth. So everything from the I mean, rocket launch to satellite motion to everything else in the real life, we need predictive model. So, for example, the GPS of Google is one of the finest predictive model based on the data which Google has collected over years. So now they know that on an average, even the road is empty, even some possible traffic may occur. In 90% case, the model of Google is working. In 10% case, it fails out. And with time, with more data, and with unprecedented situation, now Google is able to predict with even 95% accuracy. So in real life, to control the world, we need certain predictive model. And kinematics is perhaps the most fundamental predictive model when it comes to motion. So why I'm giving you this perspective? As a learner of physics, And when in future you are going to work in a different domain of artificial intelligence or machine learning or something like that, there you will learn about the predictive models, a model which can predict the future based on the input of the present. So every model is based on certain assumption. Similarly, kinematics is one of the predictive model. So it is also based on certain assumption. Now assumption will vary from one scenario to another scenario. And like you have three equations in your mind. So let me just remind you, all those three equations are part of a predictive model. In that model, the assumption which lays the foundation of all the three equations is called constant acceleration. I hope you all remember that those three equations are only valid if the model says that assume acceleration as constant. The constant also means zero velocity or zero acceleration. So if you know that acceleration is either zero or any constant number, the model will be valid. You can use that model. The moment I say that acceleration is variable, you have to disregard or discard the model, because the very assumption on which you made that model is no longer applicable. Now, why I'm saying this? Because many times I have seen students, they commit the same mistake. Whatever be the question, they start applying the kinematical equation. So please do not apply the equation if the model on which it is based, like you always create a model based on some assumption. The moment the assumption changes, you need to change the model. Else you are committing a mistake. Okay. So let me give you a formal definition of kinematics. So I will write. It is the branch of civil mechanics in which we study about motion without considering its cause. So right now we are not interested in why of the motion. Rather, if the motion is happening, if I know the inputs of motion like acceleration, initial velocity, then for a given duration or displacement, I should be able to calculate parameters like velocity, acceleration, and etc. So I'm only interested in motion, and who is causing the motion, that is of no interest to us as of now. The moment the cause is taken into consideration, the chapter will change and we call kinetics. So there is another chapter in physics called kinetics, also in chemistry also, which talks about the cause behind the motion. So in kinetics, what matters is the force, because it is a force which creates acceleration. So when you learn about motion by virtue of knowing the cause of the motion, we call it kinetics or dynamics. So both are the things that we are going to learn in a separate chapter. So our first chapter talks about motion, discarding the cause. The next chapter called Newton's laws of motion which include the cause. Now, this is the other way around. First, we need to learn the predictive model, and then we'll try to learn the cause of motion, that who causes the motion. And we know that it is the force which will cause the motion. But that's a part of the next chapter, and we'll talk about this in detail in the next chapter. Our present topic only talks about the predictive behavior based on the input already known to us. Either it is told to you or you know already, right? For example, if I say that my car can accelerate with an acceleration of maybe 6 meters per second square, so you understand that in 1 minute, what will be my velocity? Or you know already that the acceleration due to gravity is 9.8 meter per second square. So that is the acceleration that the gravity is able to create for those objects which are close to the Earth's surface, which means any object which is up to few hundred meters above the Earth's surface, the acceleration that the gravitational pull will cause will be 9.8 meter per second square. And that is like a constant which gives you the ability to predict the motion of a free falling object for a given duration and given displacement. So all these things are part of this topic or this chapter, which we call kinematics. So I hope that you all have understood why we are learning this chapter and what is the definition of kinematics. So now we can move to the next topic. Kinematics I have deleted because this will be taught separately. Okay. So now in kinematics, what we are going to learn? So in this particular chapter, we will revisit some of the concept of vector also, and from there we build the further concept. So let me introduce once again something called position vector. Notation for this vector is R. You may choose other symbol, but most of the text will report the position vector as R. Russian authors will call it radius vector. So the alternative name for this vector is radius vector. Now the question is, if you remember, what is position vector? Anyone who remembers the definition of position vector?
Sir, it is a vector representing a point in space with respect to origin.
Very good. That's the right answer. Now, if you want to start, predicting something, so you need to do some observation, and every observer becomes an origin. So when you are saying something about the behavior of motion, you become the observer, and so you also become a mathematical coordinate system with origin, which is located at your position itself. Now, why we need position vector? Unless there is no fixed origin, we cannot locate some other point in space. So, if I ask you how far is, let's say, gateway of India then this question is meaningless, because how far from where? From Kandivali, Borivali, Malad, Goregaon, or Boston, or New York, or maybe Japan, or some random location. Now, how far is meaningless? So, to make it meaningful, you need to first define the origin. So tell me, how far is Kandivali, I mean, Gateway of India, with respect to some location in Kandivali. Now, this is an essential point to begin the notation. So, every motion, you talk about some particle, some point moving, okay, and you define the origin first. And once you define the origin, then with respect to that origin, the position will be meaningful. So, position vector is the basis of all future derivation and definition in kinematics. So we need to be very good about understand about position vector, also known as radius vector. The definition is known to you, so I will just draw the line. So I will draw some origin with coordinate system, and because I know this is my origin, I can locate any point in space now. The point need not to be in 2D plane, it can be in 3D as well. So if I choose some random point P, now this particle is going to move. This may be your car, this may be a bus or truck or airplane, or maybe you and us, you and I also. The idea is the point is the entity whose motion we are interested in, and therefore we must locate it. So when you locate this particle for the first time, now this location is only for one particular instant. Now, if the particle is not going to move, then the location will be constant. But what if the particle starts moving? So now the r will be constant if particle is not in motion. But as the particle will begin the motion, the r will start changing. It means we will have something called the rate of change of r, because the point P is in motion, so r cannot be same all the time. Now, in how many ways r can move? The way it wants. But I will tell you two particular ways in which it can move, and it will make sense to us. One is the arrow will keep the orientation constant, and then the particle will start moving this way. In such motion, the r will grow in value but not change the direction. When this happens, we call it one dimension motion. One dimension does not mean that it must be okay. You can see it's the xy plane also. So one dimension does not mean that it should be along x-axis or y-axis. No. One dimension refers to that you move in any random direction, but you never change your direction. So when the motion occurs along a straight line, no matter how the straight line is oriented, we call it one dimension motion. Now it is quite possible that the point may change the direction, but again there are two possibilities. It may change the direction keeping the plane constant. So if you keep on moving in the same plane called xy plane, then the motion we call two dimension. So now if you start changing the plane, then you're changing the direction, you're going away from the origin or towards the origin, and you're also not confined in one particular plane. In such scenario, the motion is called three dimension. So can we have motion more than three dimension? Maybe possible, but we will not go into the other dimension than three. So we will restrict our understanding up to three dimension, and all the visualization technique that we can probably draw is only meant for up to three dimension. So one dimension means you move without changing your direction. Two dimension means you may change your direction, but you keep the plane fixed. So your plane of motion remains constant. Now, is it necessary the plane must be xy? The answer is no. You can choose some random plane. The plane can be anywhere, and it need not to be only xy or yz or zx. It could be some random plane between these axes. So the idea is you can have various plane not confined to the known plane like xy, yz, or zx. So when that happens, we call two-dimension motion. And then when you do not keep your plane even fixed and you keep on changing your direction, then we call the motion as three dimension. So I hope the notion of 1D, 2D, or 3D is clear to all of you. Okay, so what is position vector? I'm not writing the definition. We know that it is a vector representing a point in space with respect to some origin. Now, origin will always give you the idea how to draw the vector. And if this vector, not the vector, if this particle starts moving on a random direction, then at different instant, the r will be different. So when I am drawing something, you understand that I am drawing for one particular instant. At some other instant, things will change. Okay. And when r will change, then what we say? So when r is variable, then only we say that there is a motion. Or in other words, if motion is happening, then r will definitely change. Okay. So how it will change? It can change its direction of motion or the magnitude or both. So when you try to talk about the rate at which the location of a particle is changing or the rate at which the r is changing, so this rate in physics has given a name, and that name is called velocity vector. So velocity is basically an alternative name to the fact that the r is changing with respect to time. So what is more fundamental, dr by dt, and we have given the name called velocity. All right.
So can you repeat for the 2D one?
Pardon?
So can you repeat for the 2D direction?
2D direction. Okay. So okay, let me just maybe I can draw something for you
Sir,
guys.
the first one was for one dimensional motion.
Mhm. One
So
dimension simply means you only change the magnitude of r. You either shrink it or extend it, but you keep the arrow orientation fixed. If it is so, it is one dimension. Is this clear?
Yes, sir.
And if you do not keep the arrow, the head in the fixed direction, and if you change its direction, then there are two possibilities. It could be a two-dimension motion, or it could be a three-dimensional motion. So for the motion to be two-dimension, it should at least preserve the plane of motion. And the plane need not confine to just xy, yz, or zx. A plane can be any random plane. Let me show you in GeoGebra how the plane could be. Give me some time. So I hope you can see a new plane. Now this is the typical XY plane. And you can see that this plane, which is very fainted shade, this is neither XY plane or YZ or ZX. It's something random. Can you see that?
Yes, sir.
The idea is, if the particle is confining its motion in any random plane, this will be your, so any plane can be 2D motion. So for 2D motion, the particle just move in a fixed plane. All right. So the plane need not to be x, y, or y, z, or zx. it will be any random plane. Just okay. All right. So I hope you have understood what is the meaning of 2D motion and what is 3D motion. When I cannot even draw a plane which will confine the motion, it means it can keep on changing the plane. Okay. For example, if I write A and maybe I can add, don't know how to do this. Maybe. Anyway, so let me go back to the our original slide. So the next is, so we are already knowing the position vector. So how we write, if the coordinate of the point P is x comma y comma z, then how we write the r vector? X I cap, y j cap, and z k cap. So the mod of r is equals to x square plus y square plus z square. So now next what we need to learn is called displacement vector. So what is the displacement vector? So we put a delta symbol before the r. So anyone can tell me what is the displacement vector? So let's say you are here and you choose some random path and you reach a new point here. Now, whatever path you may have taken to be at a new location, that doesn't matter. So if I ignore the path taken by you, if I only look at where you were and where you are, then you can easily see that a single line will do the job. So displacement vector is a vector which points from the initial to the final destination, and the length of this segment is called magnitude of displacement, and the arrow gives you the direction. So displacement is all about initial point of journey and the final destination. It doesn't matter how you arrive at the destination. So why this is so important? So for any observer, when I saw you for the first time, I found the particle here. Then after a while, when I again try to trace you, then I found you here. So the first arrow is called the initial position vector, Ri, and the final arrow is called final position vector, Rf. So the green line is called displacement vector, delta R. And these three things are interrelated. So we know that the displacement vector we can easily get if we know the initial position and final position. Okay. So using triangle or what we can write?
Sir, sir, it will final position vector equals to delta displacement vector plus initial position vector.
Yeah. So if you apply the triangle law, so it is obvious that you were at this location and then you suffered some displacement. So the initial position plus some displacement will be always equals to the final position. And therefore, if I want to write the displacement itself, I must write R final minus R initial. And from here we get the definition of displacement as well. So how to define displacement vector? So it is defined as change of position vector. That's the definition. Okay, so it is not what you learned in high school. So that was the definition which was incomplete. And for the small kids, it was sufficient. But now you need to understand that displacement is having a definition. And because it's a vector quantity, so definition must be in terms of vector. So it is defined as the change of position vector. What is this? Is what we have written here. Delta R equals to R final minus R initial. Now you can also write in terms of coordinate. So if we call the initial point having coordinate x1 or x initial, y initial, and z initial, and f is, let's say, x final. So therefore, the delta R will be equals to and this will be like x final minus x initial I cap. All right. So this is how you can write the displacement. And to find the modulus or the magnitude, you can just write the old way of writing. So we can write x final minus x initial whole square. So let's take some example. So if you go from 1 comma 1 comma 2 to a destination or 3 comma 2 comma 0, so how to write the delta r? Tell me guys. What is delta r?
Sir, two.
2 what?
Sir, it's 3.
Sir, two I cap
2 i
then
cap.
plus one J cap
Yes,
minus two K cap
very good. So the delta
and
is
magnet.
pretty, yeah, just subtract each coordinate by similar coordinate together and then just write ijk. And we always subtract the initial from the final. So the arrow will tell you which one is final. So 320 is
So
final. So
final
you
to
are going,
initial, no?
yeah, so final, this is final, final to initial, like initial from final. Like the way you are interpreting is different. So what I'm saying is you find the dispersion by subtracting initial coordinate from the final coordinate. All right. I hope this is obvious.
Yes, sir.
So therefore the modulus will be how much?
Three.
3.
Correct. It's 3. So now this is the definition of displacement. And now we can go to the next definition. Okay. Something which is very interesting. So now I will define something called relationship. Or maybe I can do it later on. Not now. Not the right time. Okay. So what we can define further? So I will define something called distance. Now distance is a scalar quantity and it does not need a vector to be defined. So what is distance? It is pretty straightforward. The length of path. It is defined as length of path traversed by a part. So it is defined as length of path traversed by a particle. So that's called distance. And generally we use the symbol S. In other context, S could be displacement magnitude also. So you need to understand from context whether S is the length of the path or the length of or the magnitude of displacement. Both, could be used interchangeably, and the meaning must be inferred from the context. All right, so distance is a very simple definition, and then we can go for the speed. So what is the definition of speed? It is defined as
Rate of distance covered.
defined as a rate of distance, rate of change of distance, you can say. Okay, now whenever we define the speed, we can use some symbol as now we. So every definition will have two category actually. So we can call speed into two parts: average speed, and how we define the average speed. We write VAVG, or we write just in this triangular bracket or angled bracket. And when it comes to the average speed, the definition is pretty obvious. What is the definition? Total distance traveled upon total time taken. And it doesn't matter whether you were moving with constant acceleration or variable acceleration, constant velocity or a variable velocity. What matter is at the end of the journey, what was your total distance traveled and how much time you took to accomplish that journey. So the distance you can read from the odometer of the car. So you can read how many kilometers it has run, and then divide by the duration. And the duration may include the break also. So while going for a journey, on average, you're talking about what was your speed. So you travel for 1 or maybe 2 hours, and then you took a break for having some snacks. So you were, of course, not driving for that duration, but the journey will add that duration also. So when we are calculating the average, the duration will include everything, whether the motion is happening or not, doesn't matter. So the average speed is simply defined as the total distance traveled and what was the duration of that journey, and that will also include the rest time also. You cannot exclude it. So when you define in that fashion, we call it average. Okay. So the obvious definition that we should look for is called instantaneous speed. So that's something interesting. So for this, we use a symbol only V. We don't put a angle bracket. So what is instantaneous speed? So you may have some random curve. You are tracing some random curve, and at one particular instant, you are moving this way, the tangent to the path. Now there is one very important concept that you must understand. When you say this yellow line is my path, then what is obvious is that the direction of motion will be always tangential to the path. So this is something like obvious. I mean, no need to say something. So now this is called the direction of motion will be always tangential to the path. And the arrow which you're looking right now is actually called velocity vector. But we'll talk about this later on. Now, what is instantaneous speed? Anything instantaneous in physics is the average of a small duration. I think I have explained the word instantaneous in calculus. Okay. So what is instantaneous? So it is the average value taken for a very, very small interval. So maybe from here to here on. So if I keep the duration very small, then how much I will travel?
ds.
ds. Will travel a very small value ds. And therefore, the limit delta s tending to 0, or not delta s will be not aware. S tending to 0, what am I? Duration. The delta t tending to 0, the delta s upon delta t will be written as ds by d. So the total distance traveled upon total time taken is called speed. But if you reduce the duration to 0, we call it instantaneous speed. Nothing big thing. We have discussed this already in the dy by dx as a rate measure. If you have no idea, you can go back and revisit the video. So the v we can write as ds by dt. This is how we write the v. Okay. Now when we write like this, we call it instantaneous velocity. And from here, we get another notion. The distance we write as instantaneous speed into time. So sometime we are going to use this method also to calculate the distance in terms of integration. Now these things are again will be part of our discussion in future.
Sir,
Yes.
sir, the ds by dt is the instantaneous velocity or speed.
Speed, instantaneous speed. This is not velocity. Velocity is a vector. So what you need to again learn, in fact, relearn, because that notion will not come to you naturally. But everything which is vector must be defined in terms of vector. So maybe in high school you defined even a vector as a scalar, but I will request that do not carry that notion in JE preparation. It will be disastrous
Sir, so
if
it will
you
be
carry forward.
displacement vector by dt.
Yeah, exactly. So when things will go this way, you have to just to change the definition and you have to stick to the original definition. Okay. So everything should be defined in terms of vector and vector only. Okay. All right. So let's see. This is the instantaneous speed. So now we are going to learn something about velocity. Now we are good to go with velocity. So what is velocity? First of all, it is a vector quantity and therefore it must have a vector definition. So velocity is defined as rate of change of displacement vector, it is defined as rate of change of displacement vector. So now there is no mathematical formula for velocity. Formula is only for two things. One you call the average velocity, another you call instantaneous velocity. So we'll see those two definitions further. So mathematically, we first will define the average velocity. Now try to pay the attention that how the symbol will change. So average velocity I'm going to write as v with vector sign and then the angle bracket. And this is entirely different from the previous notation. Here, what is missing? The arrow is missing. And you have to be very careful with and without arrow. So with arrow is velocity and without arrow is speed. And the average velocity we called or define as net displacement upon total time taken.
So why do we put those brackets like that?
That's a easier notation for average. Like either you, how I will come to know whether V is representing average or instantaneous. So there should be some way to communicate, right? So either you write AVG or if you are putting between the angle bracket, then I will come to know that you're talking about average value, not the other value. And this notation is being used for a very, very long time. And so we are also trying to learn this notation. I hope this is clear. So the average velocity we define as net displacement upon time taken to produce that displacement. When you are solving problem and finding the average value, you must add all those time for which motion has not occurred. So all the rest time or the break time of journey also included in calculation of average. Therefore, if you read the denominator, you will it is the total time taken to produce that displacement. So how much time it took to have that displacement? All right. So we can write mathematically as delta R upon delta T. So we may write as R final minus R initial upon you may write like this. So there are various ways to write. If you want to write in terms of coordinate, so you may write V equals to x final minus x initial I cap okay, so you can write like this also. So the average velocity is all about the total displacement upon total time, nothing more and nothing less. So now we'll go for something called
Sir, I want to know the previous page.
yeah. Tell me what is the doubt.
Sir, I want to note it.
Pardon?
Sir, we want to note that last point.
So note. So where the doubt? You said you have doubt.
Sir, no, I said I have to note.
Okay.
Sir, done.
Okay. So the next is obvious thing, instantaneous velocity. So for any given path, the instantaneous velocity is the tangent line which you draw to the path. So for example, if I draw a line here, this is representing the direction of instantaneous velocity at that location. So if you come here, it will be like this. At the beginning, it is like this. So every arrow which we draw on the path of the main body will give you the direction of instantaneous velocity. Now you can see something easily. If a path is a curved path, the arrow will keep on changing. But what if the path is a straight line? The arrow will keep the direction constant. So the instantaneous velocity is defined as the rate of change of this arrow. Now, when we say the arrow has changed, there are two cases in which we say if the length of the arrow has either increased or decreased, that is, the magnitude has changed, or the orientation has changed, the direction has changed. So, for vector to change, it is not necessary that it must change in value. So, generally, this notion is carried forwarded with most of the students that when we say change, it means the number must change. No, that's not required. A change refers to both things in vector, directional change or length change, or you can say magnitude change, or even both. So when I say velocity is changing, then what you should figure it out that is it changing by virtue of change of direction or by virtue of change of magnitude or both. So there are three possibilities in which the change can occur. Change is not confined to just change in value or magnitude. So let's say if I am driving a car and keeping the speed of my car constant, let's say 60 km per hour, and I keep on changing the direction, I keep on taking a right turn, left turn, but I am not changing the speed. So am I changing the velocity?
Yes, sir.
The answer is yes, because my arrow is always changing. So velocity definition also includes the directional changes. So you should be careful when someone is saying that velocity is changing. You need to estimate or observe carefully that is it changing by virtue of change of direction or magnitude or both. So all three cases are there. So we'll talk about what causes the change of length, what causes the change of direction. And you will realize later on that the cause, although not part of this topic, but if you try to analyze the cause, you will come to know there are two types of acceleration in physics. One, we call it tangential acceleration, and another we call centripetal acceleration. And it is the tangential acceleration which is responsible for change of length or magnitude of velocity vector. And it is the centripetal acceleration which causes the change of direction, or you can say directional changes is caused by centripetal acceleration. And therefore we also learn variety of acceleration. If you go back to your high school and recall your three equation which you all know very vividly, like v equals to u plus at and so on, and if I ask you what was a representing in those equations, which kind of acceleration was there? Was it directional
Constant.
changes or
Constant.
magnitude change? No, that is there, but was it changing the direction or magnitude?
Ma- so
So when you studied, it was one dimensional motion, and therefore at that time of learning, you were not bothered about the direction. So the formula of kinematics, which you know, v equals to u plus at and so on, the a in those formula was only meant for change of magnitude, not the direction, and therefore that a represents tangential acceleration. So you will realize that all those formulas are only meant for the tangential acceleration, not for the actual acceleration. So acceleration also having variety, tangential and centripetal. For a motion in a plane, if something moves in a two-dimensional plane, then we have two types of acceleration. When something moves in one direction, we have only one acceleration called tangential. So when the acceleration having two different components mutually perpendicular, uh, because you're moving in two dimension, then one acceleration will be responsible for the directional changes, another for the magnitude change. Both are very, very distinct and different entities, and they do not affect each other. So we will of course explore this part in greatest possible detail in a chapter of circular motion, because when you move in a circle, which is again a curve path, then you change your direction all the time.
so infinite times, no?
Yeah, infinite times in fact. And you may change your speed also, you may change the magnitude also, so that up to you, but direction is not in your control. If I give you a path which is curved, then you're bound to change your direction. There is no option. Understood? Anyway, so what is instantaneous velocity? Now we are interested in velocity. So we use a symbol just v, and velocity is defined as I said, the limit time interval tending to zero, the displacement. And to understand this, if I draw something like and let's say you go from here to here. So this is your t equals to, maybe I can say t1. This is t equals to t2, or maybe I can write like this. That's better. So this t equals to, this is t equals to t plus delta t, and we are writing this as delta r. So as the interval will reduce, the point p, maybe I can do this. So as the duration will reduce, the point q will be very close to point P. So imagine that delta t tends to 0, so Q will be almost here, right? Somewhere here. And if it is somewhere here, then this will become delta R, right? Or dr. So this we can write as dr by dt. Now you may be wondering, so you are saying this as dr because of this arrow actually. In the previous case, we wrote ds and there's no arrow you can see. So arrow means the dr will have a direction also, and this direction will be something like this. This is the direction of dr vector. The arrow is representing the direction. Okay, so dr is a special case of delta r when time interval is very small. What also you need to realize that technically the length of this vector is exactly same as the length of ds. So if you compare lengthwise, ignoring the direction or the arrow, you can say something very clearly. What you can say from the observation on the two graph, that ds is a scalar and we cannot equate a scalar to a vector. So this is a wrong statement.
We have to take mod.
Yeah, but I can always write this. So basically the ds or the elementary distance and the mod of dr called the magnitude of elementary displacement and you can see clearly both are equal. So although the distance, if I look at the large value, if the delta t is really large, you can see that the distance is really bigger than delta r mod, right? So you can see obviously s is much bigger than. In general, s is bigger than, or maybe it may be equal to, depending on how the graph or curve is drawn. If you draw a straight line, then both will be same. But distance is always dominating over the magnitude of displacement. So when you compare the magnitude, the one length is bigger than the other length. That's the idea. But no matter how big the s is from d delta r, the elementary values cannot be greater. So they are always equal actually. That's a very interesting fact. So s may be bigger than delta r, but ds is always equals to delta r. And therefore, something very interesting happens. The ds by dt turns out to be, and this we can further write as dr by dt. And if you look carefully, that the first line is called the instantaneous speed, and second is the magnitude of instantaneous velocity, and both terms are to be same. In fact, they are same. What does it mean? It means the speed is nothing but the magnitude of instantaneous velocity. Although we have arrived at this result after long discussion, but it was already inherited in the definition of motion itself. So the is the instantaneous speed, not in general. The instantaneous speed always represents the magnitude of instantaneous velocity. For big interval, the relation will not hold true always, but it is always true for the smallest possible interval that is delta t tends to 0 without any exception to it. So let me write down as a note. So what we should write here? Instantaneous speed is always equals to magnitude of instantaneous velocity. Now what you need to realize, so that these two terms can be used interchangeably. And also remember one thing in kinematics, which is normally you shouldn't forget very easily. You cannot compare a vector with a scalar, but you can always compare their magnitudes. So you may take a 10 rupee note and buy a vada pav. So you can eat the vada pav, but not the 10 rupees, although they're equal in value. So a vector and a scalar cannot be same. So they may have a same value, but they are never equal. So when we compare the two things, we always compare the magnitude part of vector with some scalar. If I want to compare, we should never compare a vector with a scalar. That will be a biggest blunder. So I hope this is clear to all of you. Is this clear, guys?
Yes, sir.
Okay. All right. So now we are done with velocity. So let me introduce you something called acceleration. And then we'll do the sum for today. We'll not learn something new. So let's go to the acceleration. So before we solve or define something, we need to understand what we mean by acceleration.
Sir, dv vector by dt.
Sir,
No.
no, that's okay. D square V upon dt.
Sir, d square v by dt square. So that is also same only, no dv.
No.
Sir, dv vector by dt is same only, no d2.
So my question is, what is acceleration? What do you mean by acceleration? Don't say the formula. What do you mean by
Sir, change in
acceleration?
velocity.
Sir, rate of change in velocity.
Rate of change in velocity.
Yeah, that is the right definition. So velocity, okay, the rate of change of velocity is the acceleration. So now tell me, in how many ways we can change the velocity?
Sir, changing its direction, changing its magnitude, or changing both.
Correct. And therefore, because there are two ways to change it, one by direction, other by magnitude. So there are two types of acceleration. So we'll discuss about it later on. But when we say acceleration, the action which I have written here is not the same as what you learned in your high school, like v equals to u plus 80. So in v equals to u plus 80, the a does not represent acceleration, rather a component of acceleration called tangential acceleration. So this is difficult to realize at first go. So the acceleration is not always same what you see everywhere. In different context, the acceleration will change. So there are two types of acceleration. I'm emphasizing again and again for the very obvious reason that in the coming chapter of circular motion, I need this notion of acceleration. So acceleration is about the ability to change the velocity. Now the question is, can we see the acceleration? Is it a visible thing? Can we see acceleration?
No.
Sir,
Yes.
sir, the acceleration to acceleration, we are talking about the constant acceleration and the variable acceleration.
No, no, no. That's a different thing. Acceleration is, yeah, acceleration in two dimension is always variable. Acceleration is constant only for one dimension. So in one dimension, you exclude the direction point, and therefore the acceleration in one dimension becomes tangential itself. So you can say in one dimension we have only one acceleration, not in general. Okay. So far, if you have, if you will learn one dimension, then even the acceleration will become tangential itself. But in two dimension, when we learn acceleration, then we have to be careful. So one dimension, no issues. Two dimension, careful. A will have two types for sure: tangential and centripetal, which you might have heard in class 9th or 10th. Anyway, so what is acceleration? You said it, I think already. The rate of change of velocity vector. It is a rate of change of velocity vector. That's it. There is nothing more and nothing less. So again, even the acceleration will have two definitions. First, average. So you can again write as A, like this bracket, and mind you, there is no scalar component of acceleration. So like you call it speed uh, and velocity. There is nothing like a scalar value of acceleration and acceleration. So acceleration is always vector. Okay, so you cannot define the rate of change of speed as acceleration. No, we call it tangential. Of course, we call it the rate of change of instantaneous speed as tangential acceleration. But that's a very different definition. So acceleration vector we define as final velocity minus initial velocity upon time duration. That's it. Very simple. I should have written the other way around. Delta V upon delta T. So what is instantaneous? What is instantaneous acceleration? So limit time interval tending to 0, delta V by delta T becomes dV by dt. Okay. As of now, I'm not deriving it, but I will tell you that mod of A is mod of dV by dt. But this is not equals to d by dt of mod V, because I have seen this mistake committed by many students. These two are not same thing. If you read the middle term, it says that, how to read this? It's the modulus of rate of change of velocity. That's interesting. Look at the third term, the rightmost. It is the rate of change of modulus of velocity. Can you read the same? Can you see the difference between these notations?
Yes, sir.
So the middle term is representing magnitude of rate of change of velocity. So first we define the rate of change of velocity, then we take the modulus. And the last term is calling the saying the rate of change of, because d by dt means rate of change of what? Of the modulus of velocity itself. And these things are very confusing for many students. When you see for first time, you will get confused.
Sir, I also didn't understand.
Pardon?
Sir, the modulus for the third, which is not equal to d, the modulus of d vector divided by dt. So, sir, it is nothing but equal to dv by dt, and dv by dt is nothing but acceleration. So, like it is so modulus of acceleration vector is equal to normal acceleration in magnitude. They are equal. No, sir.
So the last term is representing what? Last term is representing rate of change of speed, because mod of v, if you remember, is speed. So basically the third term is just a minute. The third term is dv by dt. And this is having a name actually. So we call this as tangential acceleration. And what you need to realize that acceleration is not same as tangential acceleration. They are different. In one dimension, it turns out to be that they become equal in magnitude. So that's a very, huge coincidence. But in general, acceleration and tangential acceleration are different entities. And
So
to
first one
realize
is
this,
normal.
pardon?
First one is normal acceleration, that
Yeah,
dv
first
by
one is that.
dt.
Yeah, d by dt is the a very plain definition of acceleration. Instantaneous, not acceleration, instantaneous acceleration.
Sir, so the sorry, sir, so the dv by dt,
Mhm.
sir, it is means like means it is the acceleration only, no, normal
No,
acceleration,
no.
instantaneous acceleration.
So which term are you talking about? The last term or the first term?
Last term, sir.
No, last term is not acceleration. Last term is tangential acceleration.
Uh,
So I will tell you something. If you are moving on a curve path, then at every instant you may have two axes. One along the tangent, and other I need to draw like this. This is called perpendicular. So acceleration along the tangential direction is called a tangential, and this is called a centripetal. So what is acceleration? So when you are talking about the acceleration, this is the acceleration. We are calling a. Now let me call a vector. Now what you need to realize, this a is defined as delta, dv vector by dt. But this is defined as dv by dt. And this, if you know, it's a v square by r, something like this. R is the radius of curvature. That just leave this part.
so a centripetal is the normal acceleration.
Yeah, a centripetal is called the normal acceleration. Normal means perpendicular. You mean normal means perpendicular, right?
Yeah, sir.
Yeah. So this is called the normal acceleration. That's correct. So now, if you look at the diagram of acceleration, you can realize how the terms are different. Okay. Now imagine the line is a straight line. In such case, AC will vanish. So you will left with only one acceleration, AT. So in such case, the mod of A and AT will be equal. Now this is one particular case actually called one dimension. And that is why when you were learning the one dimension motion, you never cared about the differences. But now since we are learning 1D, 2D and 3D, all types of acceleration, we need to be careful. But this is what I'm saying. So A, AT, AC, all are different. They are not same. The one which is along the tangent we call AT in two dimension, and perpendicular to it we call AC. I think there should not be any doubt in this, looking at the diagram at least.
Sir, I have a doubt.
Yes.
Sir, acceleration.
Okay, what is acceleration? It is the ability to change the velocity, right?
Sir, I was asking that acceleration in the vector form and the normal acceleration has the same magnitude if velocity in normal form and means in magnitude of vector velocity in normal velocity and time. So
I think the question itself is ambiguous. Like you need to first clarify what you are saying. Normal is normal. Like normal is the perpendicular normal, or normal is
so no,
normal.
not that. So no, not that acceleration. Sir, I am asking that the say the acceleration which we know, which is v by t, which is like not vector form, and and the acceleration uh, for
No, no.
vector
When,
acceleration.
when you are saying dv by dt, you are talking about the scalar value, right? You are talking about the speed, right?
Yeah, sir.
Yeah. So
Yeah, sir.
that is the speed is called tangential acceleration. So it's very much obvious, I will tell you. So let's say you're moving on this curve path to speed up or slow down. How I must kick you? In which direction I should kick you? This way or this way?
So can I repeat the question?
Let's say you're moving on this curve path. Imagine you're moving on this curve path. So your instantaneous velocity vector will be along the tangent, right?
Yeah.
Now
Yes, sir.
if I want to speed you up, if I want to increase your speed, how I must apply the force? In which direction?
80.
Exactly. So to change the magnitude, the acceleration must be along the tangent. And that is why what we have written here, the AT is defined as the rate of change of magnitude of velocity. And we all know that the magnitude of velocity is nothing but the speed. So this term and this term are same thing. The rate of change of this term is actually equals to this term. So we can interchange the mod v by only v, because we have discussed already on this page the idea between speed and magnitude of velocity. They are same if it is instantaneous. Try to digest this information. Is this clear?
So my last doubt. So is mod of a vector equals to a?
No. Mod of A is only the length of vector. A is a vector with the direction. So how you can compare the two? How can you write this as equal?
So like before we wrote v equals to mod of v vector.
Yeah, you can write
in-
V equals to mod of V. You cannot write V vector equals to V.
So no, I was
You
asking
cannot.
that only.
What only? So you are saying,
Sir, a vector equals to a mod of a vector equals to a. Yeah, that only I was asking.
so there, yeah, of course, there is no problem with that. But this is not 80. This is the length of the vector only. So this, the length of this arrow, the orange arrow, maybe whatever color, this is A only. Okay. So I think accession has created a lot of confusion, isn't it? Is this clear, guys?
Yes, sir.
Okay. Okay, so access, of course, don't worry. See, we are going to learn accession, of course, in detail in future also, but we'll see how and why these things are so important. So now, before I go to the numerical part, and I need to finish one more definition. In mathematics or in physics or in your life, the average and the instantaneous always have a relationship. So now I will introduce the concept of average versus instantaneous relation in every aspect of physics or mathematics. It's a very general notion. So that's why I wanted to put as a separate topic instead of putting into the equation separately. Uh, okay. So relationship between average value of anything versus instantaneous value. Instantaneous value. So why we need to define something like this? You can think that if you know the property of motion at every instant, then definitely you should be able to predict the average behavior. For example, if I know how much a daily wager is earning every day, so let's say he earns 100 rupees on the first day and then 200 on the second day and then 50 rupees on the third day. So if you give me information about every day, I can tell you at the end of the 3 day what was his average earning. 100 plus 200 plus 50 upon 3. Now this is how you define the average, isn't it? Similarly, whether we talk about the instantaneous velocity or acceleration, if I know the instantaneous value, I must be able to calculate what the average value for the given duration. This is obvious thing. Like if you know everything about every instant, then you should know and at least you can predict the big event. That's very obvious thing. Like it's not a big deal. Therefore, so first we relate the what I'll do is I'll just find the, let's say a mathematical function is given to you y equals to fx. So what is the average of y? That's something that we need to understand. So the average value is integration y dx upon dx. That's over. So fx dx. This is how we define the average of any mathematical function. If you know the function and if you know on which variable it depends, you integrate with that variable and divide by the. So what it represents geometrically. So the numerator, it represents a geometrical area. So let's say if this is the y, x, and this is the random graph. So this graph is called y equals to fx, and you are looking for area or the average value. So you can see the y is increasing, decreasing over the duration x1 to x2. So I want to find the average height. This is the like finding the average height. What is the average height of this graph? Because y is not the same every time. Y is somewhere here, then going above, then coming down above, like this. So y is changing. So on an average, what is y? That's the question. Okay. So it turns out to be that this is nothing but the area under the graph upon the segment, the length of the independent variable for which you want to calculate it. So you calculate the area and then you divide by the limit, and when you divide by the limit, you get the required average value. So this is from x1 to x2 divided by dx from, and it is for any mathematical function, not confined to just velocity or acceleration. In entire physics, whenever you come across any mathematical function, you can proceed. Now, every time you won't get a relation between y and x, the y can represent something and x can represent something. You have to extrapolate accordingly. So I'll give you some example. You can understand. So the first thing is instantaneous velocity versus average velocity. How to define? So we'll start with the instantaneous value. So we know that v vector is defined as dr by dt. Always begin with the definition, not your own idea. So don't use your ideas, use the definition. And therefore we can add this implies the dr, we can write as v times dt. Now if I integrate both sides, the left side I can write as delta upon integration, and the right I can just leave like this. Now we will go back to the average value. Definition says delta r by delta t. But we just saw the delta r we can write as v dt, and delta t we can write as integration of dt. And now it is matching the format. You can see here, same format. Now instead of dx, we have dt. Why? Because it depends on time. So the variable can be anything. So you can see that average value will follow the pattern which I just explained. So can we have a geometrical view of this? Yes, but the graph we can only plot for one dimension. So the geometrical view is only for one dimension. If you want to plot a graphical view, I need to first fix the direction of motion, and then probably I can plot. Can you plot a graph of vector? The answer is no. We cannot plot a graph of vector. Graph is only drawn for the numbers, and numbers only talks about the magnitude. So you cannot draw a graph of a vector. You can draw the magnitude of vector on a graph paper, but you cannot draw a vector actually itself. Okay. All right. So I will not plot this.
So do we have to copy that y part also?
Yeah, of course you have to copy that.
So can you please show the screen?
The y part is even more crucial than the part which we have written below. That is for the entire mathematics and physics. Everywhere you can apply that formula. So can you guys tell me what should be the relationship between average acceleration versus instantaneous acceleration? Can you tell me?
Sir, average accel. Sir, sir, hello.
Yes.
Sir, I got disconnected. Yeah, sir. Sir, the relation between average velocity and instantaneous velocity is delta r vector equals to average velocity into integration of dt, which is t.
No, that's not.
Sir, but if you multiply integration of dt by to if you multiply integration of dt to average velocity, then it is equal to delta r vector, no?
If you multiply with,
Average velocity.
see, I mean, are you using two different speaker, because that echo is coming? So maybe uh, you have two simultaneous
Sir.
devices. So mute the device first. One of the device.
Sir,
Yeah.
now is it?
No, it's still not working. I mean, you have to mute the other one.
Sir,
The speaker.
no, actually,
Your device should not be nearby.
sir, please will you wait 1 minute? So, sir, now is it coming clearly?
Yeah, tell me.
Sir, so the relation between them is average velocity multiplied by time is equal to delta r vector.
Yeah, that's right. That's right. No problem. Yeah, so the total displacement is equals to average velocity multiplied by the total time. That is okay. That's fine. So what is your doubt? I mean, like I was looking for the doubt part.
Sir, the left part,
Mhm.
sir, the y is equal to f of x here, sir. What y and x denotes?
So y is the you can think like a instantaneous height. Like if you are here at x, what is your height? This height is y. But as x will change, the height will change, right? Isn't it? So is the height same for every x? If I choose a random point here, do you think that the height will be same as before? Is this height same as before? The answer is no. And so the question is, what is the average height? Because it's increasing and decreasing. So on an average for the duration of x1 to x2, what is the average value of height, or you can say y? So every mathematical expression or even a vector expression in essence represents the same thing. Okay. All right. So now we should go for next concept. So what is the relationship between instantaneous acceleration versus average acceleration? So means a versus like this, the average value. So what is the relation? So we know that we start with the average first. Sorry, instantaneous. So we know that a vector we write as dv by dt. Therefore, dv turns out to be a times dt. So the elementary change in velocity is a multiplied by elementary duration. That's obvious. And if you integrate both sides, the first term will give you a big change, because when you add small changes, what you get is called a big change. So we call delta v, because the integration is like addition. So when you add small things together, you get a big thing, and this is equals to a dt. That's the first thing. And now coming back to the average definition, it is delta v upon delta t, and we have just learned delta we can rewrite as this, and delta t we can again write in integration symbol. Now this is matching the first definition. Understood? So the average and the instantaneous will always have this behavior. The more you dig into the, when you look at the one dimension problem, we can actually give you the geometrical perspective. For vector, I cannot draw a graph. Now you will realize the mathematical graphs only relate two numbers, the x number and the y number. But a vector depends on various number, like vector is xi cap, yj cap, zk cap. So if I draw a three-dimensional vector, how many number it will have? Three set of numbers, you can think of. And because it will have the three sets, so I need to plot three graph for one vector. Now I'll just try to explain you what I mean. Someone is trying to plot a graph between v versus time. That's impossible. Now what we know that the v vector we can write as vx I cap, vy j cap, and vz. Now this is also very important skill to pick. So v equals to vx I cap, vy j cap, or vz k cap, and we have actually, although it looks like one variable, but if you look deeper inside, you see there are three variables. So how can you plot three variable versus one variable? That's impossible because no mathematics will allow you to do that. And therefore, you need to realize we cannot plot the graph between v vector and t. This is a totally blunder. But what is the solution for that? So we may plot vx versus t. That is allowed actually. So for one vector v, I need to plot actually three graphs because there are three variables. Now realizing this is difficult for any beginner, including me also, but this is something very, very interesting to understand that you cannot plot vectors because the mathematics that we know never allow us to do that. So we always plot scalars or numbers. And because I am defining here a three-dimensional vector, so one vector is equivalent of three graphs. For two-dimensional vector, how many graphs? Hello, anybody there?
Yes, sir.
So now you are seeing that if a vector is three-dimensional, so how many graphs we need to plot?
3.
3,
So for two-dimensional, how many graphs we need?
2.
So now you must be realizing that only for one dimension we can plot the graph directly, right? So for one dimension, we just need one graph, and that is sufficient. So when you plot the graph of v equals to u plus at, then here it is understood that the v and the u both are one dimensional. So that's why you are able to plot it. So you cannot plot a vector versus a scalar graph. That is what I'm trying to explain. You cannot plot v vector versus t graph, but you can plot individual component of velocity versus t graph. That is possible.
So, hello, sir.
Yeah, tell me.
Sir, I didn't understood the V and U part.
So v is a velocity vector called the final velocity vector. U is called the initial velocity vector. Okay. So the v and u must have same direction, right? At least along the same line. So if we have a v in a different direction, then u actually it's a two-dimensional motion, or at least two, or maybe it can be three also. So in one dimension, whatever you write u or v, they remain along the same straight line. In worst scenario, they can reverse direction with respect to each other. So one is going right, other is going left. But they remain confined along the same straight line. So it's one dimension motion.
Sir,
So for one dimension, you can plot a graph between the velocity and time. This is what I'm saying.
so sir, we cannot in one dimension we cannot plot V velocity and time graph.
No, you only plot the magnitude of velocity and time. You don't plot the yeah, you can plot any vector. I mean, like in one dimension we have the freedom to plot, and what we do is in one dimension, because direction is not the issue, we have only right or left, up and down. So what we do is technically the direction part we will remove and will introduce a sign convention. That's like easier way to deal with the direction. So when we learn one dimension, The arrow part we will remove. Actually, we'll just avoid the writing arrows because it is cumbersome. So what we do is we take care of direction with the help of plus and minus sign. So when we are going to learn the one dimension, this is what we are going to apply. So one dimension is not a scalar. One dimension is also a vector, but conventionally we remove the arrow sign and we take care of direction by putting plus or minus. So when you write v equals to u plus at, or when you write v equals to u minus at, the difference between the first and two cases, in the first scenario, u and a are pointing in the same direction, but in the second scenario, u and a are exactly opposite to each other. So that is the idea we take care by sign convention. So when we will learn the one dimension, I will tell you how to use the sign convention. So that we will do later on. So of course, don't worry. So now I hope the
Sir,
notion graph is clear. Like why we plot a graph and how many graph we need for every vector. Yeah, tell me.
so can you repeat?
Pardon?
So can you repeat for that U and V graph, please?
No, no, there is no graph between u and v. Graph is between v and t, time and
Ah,
velocity.
V and T. Sorry. That.
Yeah. So tell me what you want.
Sir, can you repeat what did you say in that part?
Okay, don't worry. So don't worry about graphs. Graph is a separate topic that you will learn. So we will dedicate a complete one on in fact two lectures only for graph. Okay. So we'll discuss about graph in detail when it comes, the right time will come. So right now we are done with the basic definitions of velocity, acceleration, displacement, position vector, the average, and the instantaneous relation. And all these things are the prerequisites to learn other motion. So now time has come to solve the question actually. Okay, so we have done with all definition. So now let's do some problems. Okay. So what kind of problem we are going to see? I think time is okay. Okay. So we don't have time. So I will take one question before I end this lecture. So this one problem will explain various problems. Like this example is still a big example. So imagine we have a circular path. So I'm choosing the two-dimensional motion to begin with. Because the path is circular, then one thing is obvious, that velocity cannot keep the direction same. The velocity will change for sure because of direction, at least, isn't it? So if you are
Yes, sir.
moving on a circular path, your direction will always changing. And because direction is changing, so you must have an acceleration. Okay. Now I have no idea whether the speed is also changing or not. If speed is not changing, then you will have only one acceleration called centripetal, because uh, centripetal acceleration helps in changing direction, and tangential will help in changing magnitude. So when I say a particle is moving with uniform speed on a circular track, it means which acceleration is absent?
Tangent.
Tangential. That's the right answer. So which means that tangential acceleration is absent. So there is only one acceleration called centripetal. So the A vector which we used to write, the A vector will become centripetal only. So they will become same if the V modulus is constant. Okay, so we'll come to that. So let's start solving a problem. So let's say a particle is traversing a circular path of radius r, and it goes from the beginning to a new location here. And in doing so, let me remove this arrow now. So you start from here. Your journey ends here for the duration, not ending. You may be continuing, but I'm taking only start and end. And this angle is theta. So the first question first, a simple question. What is the modulus of displacement? It's a simple geometric problem. So the modulus of displacement means what is the length of this line? That's it. So you do not need a concept of vector, but even you do not understand vector much, can you find this length between the start and the end from the given geometry? Or what we need to do to solve in terms of vector? To solve in terms of vector, we need to think of position vector. And to draw position vector, you need to have origin. To have origin, you have to choose somewhere which is convenient to you. And I think the most convenient place in the circle is center. So I will choose the center as my origin, and I will draw the initial vector and final vector, and we'll use the concept of vector to get the length of that line. So can you try this? Anyone who is interested in solving this question? Or shall I go ahead and solve? Tell me quickly. Okay, done, guys.
Sir, no, last step.
Okay.
So can you solve this one?
So my answer is r
Yeah.
under root 3 minus 2 sin theta minus 2 cos theta.
Oh my God. This is something dangerous. Never seen
Sir,
before.
I took the origin at the center and I found I got the components of position vector of
Okay, okay, no problem. So,
both and
okay,
then I solved.
yeah. If I call it Ri, if I call it Rf, so first I will solve in the vector method, then I'll solve by common sense. This is called delta, right? So from triangle law, what you can write is delta R vector, not magnitude, vector is R final minus R initial. And now it's a modulus will be mod of R final minus R initial. And we know from the difference of two vectors how to solve the difference. So what is known to us? We know the length of each vector, which is R, and the angle between them is theta. So the difference will be under root of what? A square plus B square minus 2AB cos theta. A square, B square minus 2AB cos angle between them is theta. So the answer is 2R square 1 minus cos theta. This is the answer. Now you can take R outside. So you get 2 into 1 minus cos theta. But this can be simplified further because we know that 1 minus cos theta from trigonometry can be rewritten as 2 sin square half angle. So if you do not remember this formula, there is formula like
Yeah,
this.
sir. Sir, it will be
And so from here, if you replace 2 theta by theta, it becomes cos square theta by 2. And from there you can get it. So
sir. If theta
therefore,
is very small, then we can replace it by theta by 2. No.
no, it's not very small. Okay. So theta, yeah, you can do it. If it is small, then you can do it. You can place theta square by theta square by 4 anyway. So this we can write as r multiplied by 2 multiplied by 2 sine square theta by 2. And then this
So
will,
R sin theta.
yeah. So this turns out to be something very simple. Now this is the vector way of doing it. But can we do without vector? The answer is yes. At the end of the day, it's a triangle. In triangle, I'm looking for finding the side. I do not need a vector. I just need a geometry. So I'm drawing it as a separate triangle with center as one vertex, and probably I'm calling this as R. This is theta. What I'm looking is what is the base. Now, is it difficult to find base? No,
No, sir.
it's very easy. We can drop a perpendicular from vertex to the base. Maybe I have drawn a tilted diagram, but nevertheless. And once you draw the base, it's an isosceles triangle. Then
Sir,
this
2
theta by 2.
sir 2r cos theta.
No, it's a front side, it's a perpendicular. So this will be r sine theta by 2. This is also r sine theta by 2. And therefore the length is how much? The delta r mod is 2r sine. If you want, you can write x and you write sine theta by 2 equals to x by r, right? Sin theta is opposite side upon hypotenuse. So in this triangle, r x theta by 2. I hope this is easy to determine. Okay. So you will do a lot of practice in tutorial. I'll continue with the theory part to cover the kinematics as soon as possible because it's a huge chapter. So I really don't know how many lectures is sufficient, but in one lecture we have covered the most fundamental part. So there are four parts of kinematics. One is called the 2D motion, which you just learned, like this part, vector notation. Then we come across the one dimensional motion. Then we'll go for the projectile motion. We'll go for the relative motion. So this is like four parts. We have to learn all these parts. So it's a huge chapter, and this chapter you should not learn because of chapter of physics. It's like it will develop your analytical skill, like how to manipulate equations, solve equation. So I will always recommend solve as much as possible. So almost 21 years back, when I was learning this chapter, I vividly remember I was in class 11 in 2000. This is 2021, exactly 21 years back. So in this chapter, I solved around 450 problems within, of course, a month time, 1 month or maybe more than that. It was a really huge chapter, so I was solving every day, and it's just like fun. It's like a puzzle solving. It's not like physics. So the difficult part is the vector part, which we have just finished. The rest part of this chapter is easy. So you need to command the vector part. And why we need to command the vector part? The reason is other chapters will demand vector part, not the scalar part. Like one dimension is something very easy. Two dimension is something which you need to master. Okay. So we'll see all those things in the next lecture. Till then, goodbye and take care. And guys, please be on time during the lecture. Do not come at random time. So even if your lecture is at 8, you start preparing for a connection and Zoom at 7:30, maybe 7:45. Sometimes it happens. It takes some time for me also. So generally, I start very early, and because my laptop is always on, it's not, I mean, sleeping anytime. So it gets hanged sometimes. So that's I can control. Anyway, guys, bye and take care. See you tomorrow.
Thank you, sir.